It's, I can do all the ensuing analysis will apply to it as well. So having these two discussions side by side, obviously V, a vector in the tangent space, V in TPM. So let's say that dP of M is the set of all of these derivations. Set of all derivations at P on M. Yeah, you can differentiate and return a number, the derivative at a point, or you can do whatever you like, as long as you're abiding by this rule. Do whatever you like. The set of all these actions, or linear actions, on C infinity functions that return a point, return a number, and abiding by this rule, we call it derivations. Define them the way you like. Any action you like that abides by this rule. And according to this, V in TPM is actually one of these actions, right? Any question about that? That V, a vector in TPM, is one of these actions. V in DPM. Any question about that? How? Because a V takes a function and returns you a number. The number represents the directional derivative of the function along that vector, right? And because it's differentiation, of course it will obey the Leibniz rule, the product rule. Okay? So from this we can conclude that the tangent space is just a subspace of this guy. Right? And we have the following lemma, that they are actually equal. They are actually equal. So any vector V is a derivation taking a function f and gives you the directional derivative of f along V, and vice versa. Any derivation comes from or correspond to any derivation like this. Define it the way you like. At the end of the day, it comes from the directional derivative along some V, some unique V actually, in TPM. Things may be obvious, but I need to stress it. Yes.
Why they are equal?
That's a good question. I mean,
the first you said that TPM is a subset of.
That's right. This is obvious.
Yes, this is obvious.
Very good.
But why?
Yeah. So this is why it's not that trivial. It requires a lemma. So I'm just skipping the proof. But basically, you show that the map, this very simple map, that takes, let's call it a name. Let's call it S. Okay. So it takes a vector and gives you what?
A real number.
No. It takes a vector. So this is, takes a vector and gives you V1 partial x1,
okay.
Vn partial xn. This is a vector in TPM, right?
Yes.
And this is what? A derivation. So this is a map from TPM to dP of M. You can easily show that this map is bijection, injective and surjective. I can show you that to you easily, but I don't want to waste the lecture of the time of the lecture. And if it's injective and surjective, it means that for every vector there is a derivation, for every derivation there is a vector. Okay? So, this is why in differential geometry, when we see V in TPM, V is a vector, has components, now on. We will write V as V1 partial x1, Vn partial xn, okay? Because any vector is really a derivation and any derivation is really a vector, okay? So let's now go and compute this thing. Let's go and compute the directional derivative. So we have, okay, that's right. Directional derivative of f, which is smooth, along V in TPM. Let's compute this guy. How we compute it? We have at least 3 ways of doing it. First, working in ambient space, if possible, if you like. If possible, it's not possible all of the time. So in ambient space, we will do the usual definition, nabla f dot v, and that's it. So let's take an example. We have our gamma of t from before, t half, and square root 1 5t squared over 4. So when we differentiated gamma prime of 0, we got 1 1 half and 0. And let's have a function, so say x squared plus y plus z squared. Okay? So gamma prime of 0 acting on f is simply nabla f dot v, which is partial f partial x. This is 2x. Right? So 2x and 1 and 2z at the point, which is 0, 0, 1, dotted with the vector. So you get half. This is working in ambient space. Of course, we will not do that. We will work in coordinates. So say, let's do the, we want to apply gamma prime of 0, applying on f in coordinates. Here is your manifold. Here is the coordinate chart, Rn, phi inverse. Here is your curve, gamma, and this is gamma of t. Here is your function. When we say in coordinates, when we say gamma prime of 0, what do we really mean? Or at least gamma, what do we really mean by gamma in coordinates? Gamma in coordinates means what? Phi composed with gamma. So let's consider phi to be x, y, z, just projection. So phi composed with gamma is t over 2. So from which we get gamma prime of 0 is 1.5, right? And when we say f, what do we mean by f in coordinates? What do we mean by f? What do you mean by f in coordinates?
Phi composed with
Phi inverse f.
phi inverse.
So f composed with phi inverse. This is the map that takes the coordinate to the real line. So let's do that. So f of phi inverse. What's phi inverse? If this is phi inverse of x and y is x squared, y squared, and square root 1 minus x squared minus y squared. This is the regular map, the usual map, projection on x, y. So phi inverse will give you x, give you x, y, right? X, y, and square root. Let's apply our f on that. Where is f? F is here, the first square, the second, and the third square. The first square, the second, and the third square. Okay? So this gives you y plus 1 minus y squared. This is really your f. When we say f, here is your f. When we say gamma, here is your, or gamma prime of 0, here is your gamma prime of 0 coordinates. Now let's apply the product. So gamma prime of 0 times f is 1 partial f partial x plus half partial f partial y. At the point, this is in xy coordinates, so the point is 0, 0. This is actually 0, and partial f partial y, put y equals 0, you will get half. It's the exact same number, and it must be the exact same number. If you do it in ambient space, if you do it in coordinates, and as an exercise for you, do it using phi of the stereographic projection that I wrote you earlier from E on AA. Okay? You should get the exact same thing. Okay? Any question about that? Okay. So done with direction derivatives.
Professor, can you repeat the last line? Gamma dash 0 dot f?
This is gamma prime 0.
Okay.
A vector.
Yes, dotted with f.
And this is your f now. Right? Dotted, this means what? It's not dotted in our, this is acting on f.
Acting on f.
So it's the directional derivative. Okay, in this local coordinates. Any question? So we got two means so far. You can work in ambient space. In any coordinate chart, you should get the same result, of course. And there will be a question in the homework. So let's move on and use this knowledge. We're going to define something called, actually before I move out, I'd like to say that the tangent space, TPM, if this is n dimension, is actually Rn, right? It's isomorphic to Rn. It's a vector space. It's more than a vector space, but it's isomorphic to Rn. Something that we, should we do it now? Let's try to do it because math spaces. Yeah, hopefully this. Yeah, very good. This picture, I like it so much. I actually forgot to discuss it in the math lecture, and I put it there in the notes. So yeah, this is the hierarchy that we talked about a little bit, right? We said if we have an inner product, we can have a norm induced by the inner product, and if we have a norm, we can have a metric, right? If we add completion to the norm, we get Banach space. If we add completion to the inner product space, we get Hilbert space. And you can see here, the best thing ever that you can hope for is Rn, right? The poorest thing is actually the topological space. You cannot do anything. You cannot add, you cannot multiply by scalar, you cannot do anything. It's just a poor, like a poor country or something, there is nothing. Here it's like a very civilized, advanced country that you can do anything. The manifold's here, so the manifold is not in a good state. So it's a closed topological space, except that we are lucky enough to have maps between manifold and the Rn, so we can hopefully do calculus on Rn. But still, we cannot add points, for example. Even with this, with this definition, we cannot add points. The tangent space, the manifold at any point, is equipped with the tangent plane, right? Obviously, because it's a space of velocities intrinsically or expectedly, you can add velocities to each other, you can scale the velocity. So the tangent space is a vector space. A vector space where you can just add and multiply by a scale. Okay? So this picture is already in the lecture of math, but we forgot to discuss it. Any question about that? Okay, so the tangent space is a vector space. It's actually isomorphic to Rn, so it looks like Rn. We can add vectors and multiply by scale. Now let's move on to the tangent maps. Push forwards. M, a point P, we have vector V, and we have, this is M, so this guy maps, this is N, this is M, maybe M-dimensional manifold, N, M-dimensional manifold. So this point in particular maps to f of p, right? And this vector will map somewhere. So this vector will map to a vector over there, right? Depends on the transformation. So this is v. Okay? It's not exactly v, of course, but you know it will be a vector in the tangent space. So just recall that you know this is a manifold, so we are always endowed with these coordinate charts phi inverse. This is Rm. Here we're lucky to have these guys Rn psi inverse, right? If the coordinates here are y's and the coordinates here are x's, we can really write y as a function of x, because f maps any point on M to any point in N. So in particular, it maps any point in the x coordinates to any point in the y coordinates. Okay. If we want to be precise, this will be what? What's this f of x? Y f of x will be what? How do you write it?
Phi minus 1.
Say it again. Sorry?
Phi minus 1 f.
Very good. Very good. Phi inverse composed with f composed with psi. Right? This is f in coordinates. Okay. Okay. So now I need to map. I know that f maps the manifold to the other manifold, and I need to map the tangent space. So I have V in the tangent space of M at some point, and I need to map it. Well, this is super easy and it's nothing fancy at all. We're just here giving it a different name.